Okay, hello. I will speak a bit about gene sequences and some abstract way of proving termination of gene sequences. The topic is sequences, and the talk will be related to well-path orders as a tool for proving termination of gene sequences. And I will also discuss a bit this aspect of how Goodstein sequence can be interpreted in terms of direct limits and finitary functors. Now, the whole talk will be about something very basic, so maybe somebody would consider this as a triviality. But anyway, so what are the Goodstein sequences? Well, we define normal forms for natural numbers. So you take a number k. Let's define normal form. Of number m is respect to so if m is then m then k normal form. And if n is simply as k, then we write m plus k to the r plus p. R is not this one. And p is smaller than k minus k. Yeah. Okay, normal forms can be seen as terms. So, well, this is the normal form, and the usual stuff on Goodstein is the Goodstein process, where we take normal forms. First, take number m. We represent it as a base 2 normal form. Then we move the base k, base 2, into base 3, subtract 1. Then move base 3 to base 4, subtract 1. And this is terminating. Now, we want to consider this in an abstract way. So we want to introduce terms. And what is the reason for introducing term? I want to prove termination of the Goodstein process by not by appealing to orders. So the Goodstein process is basically, well, the base change operation. This one is defined as we take the normal form of k, replace k by k. Base change in the plus base change in p. And then Goodstein says the following. So start with given number m. Then m0 is m, and ml plus 1 is he takes the normal form of m, one form of ml, and then we replace base l plus 2 by l plus 1, as long as m is positive and 0 otherwise. And square is all m else that it's 0. Now, normally this is proved by moving things into the ordinals and then showing that when get to descending sequence of ordinals when this is not terminated. Now, abstractly, the terms. Well, now I want to prove termination. I want to prove this result by appealing to well-path order. So, what are well-path orders? Let's share well-path. the partial order, and every infinite sequence I and change this I is this. Well partial orders are well founded, and linear extensions of well partial orders are well founded. Now I want to use well partial orders to prove termination of the Goodstein sequence. And there's a result by de Jong, namely that binary trees are well partially ordered under compatibility, and the maximal linear extension is ordered target from 0. So we have the set terms T, and if A and B and C, then let's say F and B. This generates terms over constant 0 and binary function symbol. And we have amenability relation, and you hear this in every term. And moreover, if S is available in the term A, then X is available to B. If F is available into B, then F is available to B. And finally, we have to close if A embeds into C, B into B, then it can embeds into O. And then this relation is in the partial order, and the maximum order type relation is equal to X1 So the idea is now not to move the Goodstein sequences into ordinals, but to move Goodstein sequences in a set of terms so that I can apply somehow this here. Now, so moving terms, those numbers known from terms. Is not at all difficult. So if you have m smaller than k, then we move it into constant cm. K itself is moved for a variable, let's say is. Okay. And then if we have m of the form a to the after, I move this m into xk in r. Let's call it embedding E. So E of M, the scale embedding of R, embedding of P. So what is the goal? The goal is I have basically several players, namely I have the numbers K running around, and there's the exponential function, and there's the addition function. And now I want to shift this into a system where I have just one binary function. If you apply this theorem by de Jong, and it's not so clear how to set up the binary functions. So here is some sort of indication that the role of K is obstructed away. So we use some binary function, namely, let's say A and B goes to x to the A plus B. That's already something. Okay. Now, if you take it in a more abstract way, so just forget everything. We define a set of terms in K, indexed by K. K is for the non-form. So if so smaller than K, then I have that I is into K, but it's a constant of term system K, so that is an upper index K value. And I say the complexity of if K, let's say that the norm of K is and the third is A and B and B. Then I say as a tree as a tree. The norm of the K and B is 1 plus the norm of K. Norm. So what do I have here? I have here a system Tk for every number K. And yeah, now I want to do an abstract base change. Okay? So I want to model the base change operation on these abstract sets. Okay? So for term T, I define K as K is by L. T. The following obvious way is R is 1 and K, C I, say, K becomes C K and L equal. And as K becomes L is L A B becomes B I replace K, right? Now what do I have here? I have systems Tk and I have a transition from Tk into Tl. Now I define O-rings on Tk, namely O-rings modeling these individual fields. And following ways, definitions of relation that we mix K on K. And we do the usual stuff, except that you have to say what we are doing with the constants here. The constants come in Boyle limits. So the first and then this you can see. Second, CS stands for number smaller than K, and they should be smaller than K. Then third, well, the Pythonian cable, okay, is composed term. Okay. Fourth one, okay. So x k is labeled into this. Then comes the clauses which are over here, namely if s individual s is individual of f a d, 6 is s is individual into e of individual k is d, and 7 s individual into a square, and e squared then f k is d individual as k. Now what do I have here? I have here systems. Okay, systems L. Here's the relation. Here's the relation. And now the question is how to merge them together. So I form some sort of direct limit of this k. Next. Well, what we do is we do now set t. If t is big, I want to put it into some union. So the embedding ik of t, the sequence, okay. Now the base change k moves to k plus l. And I consider the transfinite sequence along all L. And I declare these images of T. So T consists of embeddings of elements of Tk. Now, if you form a direct limit, then you can start at some point here, or at some point here. But when you can reach from here to here, you have to identify these infinite sequences. So also you want to have a direct limit. Okay, so we identify Tk F or the this plus by k plus L SP omega, where this is here. Okay, so this gives us a domain. On this domain T, we define the functions, binary functions in the usual way. So assume well, let's say assume we are given like this. IP prime S is in period, is in K1, and now assume possibility K1. Then I do what? Say what is F of and K S. I K prime of Well, the point is clearly we jump to the bigger one and apply the function fk prime. We take fk prime. I have to move from S into system not k, but into system k prime. So T is in Tk prime. After base change, this is in Tk prime. Fk prime operates on Tk prime. And then I move this one in the what do I do? Yeah. That's the definition of the function f. Now, what do I do with functions? Constants. Ci in the system T becomes I take k of okay. And then what I do with the variable xk and xk into the limit and call it omega. So what I did here is I have not spoken about any Goodstein sequence. I've just spoken about how to set up a sort of variable limit. Now we define what's the point here? The point here is by forming directly we have abstracted the k away. So all the functions fk become one uniform function f. F is binary. So we come a bit more into the realm of this situation. Now this is the stuff by de Jong, but there's some sort of easy modification. Namely, when you plug in here some sort of ground structure, let's say some alpha, and you declare basically that beta is available as a T for all beta more than alpha, then you still have a well-partial order, and the maximum order type in general is not epsilon 0, but a bit bigger. It's basically you go take alpha and form the next epsilon number alpha. That is what we are going to do here. We smuggle in the natural numbers, we smuggle in infinite order, and then we have a binary function. Okay, now the question is, what is our embeddability relation on the set? But it's also not too surprising. And we shift our binary relations these ones. Actually, what's important? I forgot the indices here. To have a binary relation with index k. So all cases at k. Okay. That's all fine. And then we define the corresponding binary relation in the limit, just moving all the finitary approximations into the limit. That you would expect. What was the order type that you said? With alpha. We take alpha as element structure, and then we go to the next epsilon number. So the usual result by the Schmidt would be if you smuggle in constants into binary trees, where the upper bound is epsilon index alpha, 6.3. But since we smuggle in only U elements, we can just create an epsilon structure But anyway, it should just be some ordinal which is under control, which is somewhat doable. So the next definition is basically we define the direct limit of these approximations. Yes. So we find station on E, and we do it as usual. Then we assume that S is in Q, is in K prime, and then what? EKS is embedded in K prime T. If not, so first we move S into dk prime, and then our relation. So and T. Okay, so this is binary relation, and then the next lemma is basically it behaves properly. So I is less than J, then in the limit, see I evaluates the CIs are below omega. We have that the CK omega are sitting in below all FAE. So S A plus S available A. S available in E plus S FAE, and it's F is available in S prime, T prime, and F is S is available to each. So that's interesting, and so this is a very fast model, and the maximal order type is epsilon 0. Namely, it takes next epsilon number above omega, so that is okay. Now we want to prove termination of Goodstein with this stuff. So we have to smuggle in somehow the letter numbers into this finitary system. So let us assume follow. We have a certain extension of the amenability relations. The first one is I consider TK, and on TK I have this ordering this one. So assume we have three linear ordering. This is okay on. So what does this mean? We have productivity, reflexivity, but if A is less than equal to K B and B is less than equal to K A, it does not follow that A is equal to B. Just now, what is here the idea? The idea is we have abstract terms, and different terms can denote the same number. So the idea is I want to define on dk somehow this relation A is equal to KB. So the value of A is less than equal to the value of B. Then, of course, you can have different terms denoting the same number, and then you have not this, you don't have this antisymmetry. The second one is the one we have is if S is less than to K, E, then we want to have that after base change, and this quality remains. But at this moment, it's not so clear whether it's a good idea to ask for this. So we have just abstract terms and stability after base change, stability of order and base change works to normal forms. So we demand this for K big enough. The reason is when K is big enough, then the next one comes. Yeah, K big enough is basically explaining that S and T are in normal forms. Well, that's not so clear yet. Next assumption is if S is a vector into E, then S should be less than or equal to E for K is maximum. No, S and E. And number what diagrams. And norm of S, norm of E by K. And S is less than or equal to KE, and is less than or equal to KS. So we have that this ordering less than or equal to K becomes linear when the terms are complex enough. Now the point is, when you look back at the very beginning, they wrote down terms, natural numbers, and I plugged in for K a variable. Well, when the norm becomes big enough, then the term representations become normal forms. And that's what's really happening here. K becomes big enough, and they have two abstract terms, and then they are normal form, and therefore they are uniquely denoting numbers. So what is the idea? If you have a term T, T maps to the maximum over K and the norm of T is the normal form of T. So where T is identified with all base changes in the direct limit. And in the direct limit, after some time, representation becomes unique. And that is what I discussed with Fiona, namely I want to have some sort of relators where at some moment notations are well defined, but maybe not at the beginning. In the beginning it could be some mess. Okay. That's So what's the point here? So I have the structures TK and the linear relation on TK. In every TK, I have a pre-linear ordering less than equal to K. Now I define less than equal to relation on T. Somehow the direct limit of those ones. No definition. So assume S is in K, T is in 1. And assume K is at least as big as the normal S. T. When I say the limit is like we can only if S after I move it to K prime to K prime. Now what's the point here is then this is linear ordering on T. And the reason is that if this K becomes big enough, then I have anti-symmetry. Moreover, we have this property. No, this. What do I want to have not be? Maybe this is wrong. Here's something wrong. I want to have here pointwise variability. So some sort of the less than equal to K relation should be an extension of the triangle relation on TK. Because now I want to conclude that less than equal to extends what's the point here? Now I have a linear ordering which extends with the mean relation, and therefore it's a wet. And so so typically when one applies this machinery to this Goodstein stuff, one obtains epsilon zeros in canonical way. Now, what is needed for Goodstein? One needs operation n going to n so on. Now, in the abstract setting, which I have here, I don't have numbers, I have just terms. So I need an abstract predecessor relation. So a new assumption is with the property that in the limit t is smaller than I care. So I have some abstract predecessor function on my sets t. Then I can write down what's on t.
I don't know. So do we? Okay, I mean, of course, you can do the substitution, but I think kind of in all examples we realistically have, the point is the order type of TK would be typically with just omega, or
Yeah.
and or I guess you can also consider case when it's just finite. But anyway, the point is it's kind of I think in all the examples we have like predecessor really kind of predecessor function with just natural predecessor function.
Right.
Anyway, yeah. Uh, okay, okay. No, no, but I think kind of what, okay, right. But here you can find more, right? So you want, okay, I guess you, perhaps you can define predecessor like as a slash predecessor. But what you really want is that uh, when you look at this predecessor, it will be still predecessor, kind of smaller thing in the limit.
Yeah.
Kind of actually what you, kind of what, okay.
So now we consider the Goodstein stuff. And so we start with some term P, let's say in EK or 2. And well, maybe start in P2. And P0 becomes P. S1 becomes so what? I take I replace base L plus 2 by L plus 3 by this way. Now this is a term in PL plus 3, like so this is a sort of abstract formulation of Goodstein. And then the claim is for all T for all T in TK, resistant L such that L is 0, which is the function 0. And so this definition is done if and so 0. So C0 plays the role of 0. Okay, and now the usual proof for Goodstein can be copy and pasted. And using the properties of the direct limit, you see directly termination. So what do we do? Define if let be equal to I take from L and I move into the direct limit. Okay, and now I want to produce the same chain with respect to this relation. Okay, and now then. So I show that OT L plus 1 is smaller than OTL. It's not yet 0. Okay. It's basically a one-liner. Here's what. I take P L plus 1 and I move it into the limit via I L plus 3. Now I apply the definition I L plus 3 of L plus 3 T L plus 2 is replaced by L plus 3. Now, since I have here this predecessor notion, I want to have what? I want to have one L plus 3 of TL N plus 2. And now I want to have that this is the same as my L plus 2. Okay. First moving L plus 2 into L plus 3, and then moving into the direct limit is the same as moving directly. And that's it. But this is not a deep result. It's just the old result somehow reformulated in terms of abstract stuff. But this is the old proof which we already know. Now, what's the point here? The point here is we have Goodstein with respect to the operations A, B goes to K to the A plus B. So it's basically a Germany function parameterized by K. Now we can also study functions of this form. AB goes to take is the Ackermann function of index A parameterized by K in B. It's all the function of 3 arguments. And when we abstract the K away, then we have a function of 2 arguments. Now, to recall what is the definition of it? So the Ackermann function of 0, A and B is B plus 1. Then we have the Ackermann of A plus 1, K and 0. It is A, K. Now this function is iterated, applied to 0, and the number of iterations is given by K. So it depends on K or K plus 1. It's a half of order. And the common function of plus 1 for a B plus 1 is I take the previous defined function iterated K times this argument, and then applied to Ackermann A plus 1 K. That's a bad detectives. I write it to process. A plus 1 K plus 1. Is I take A, this function, I iterate it K many times and apply the result to A plus 1 K. So I do the sum defined by main recursion on A and substitute recursion on B. So here I assume that this value is defined, and then I do the iterating on the main recursion. Now, using this binary Ackermann function, we can define normal forms. And when you abstract K away, you get a binary function. And so it seems that using this signature, you can only generate Goodstein sequences of strengths epsilon 0 by abstract results on Bell partial orders. And when you would plug in here some exponential function, and you define normal forms in terms of well, then these function values are spread out. And then you have to fill up the course in between by exponential terms. And basically, you need two binary functions to represent your normal forms. And this leads to very binary orders. You get upper bound gamma 0. And with David van der Stuke, we already proved some result which reaches the strength gamma 0 using these functions. Now, this is an upper bound, but not a lower bound. When you choose the wrong normal forms, some of the strings collapses and gets downwards. But what I want to stress in this approach is you get theoretical limitations on your signature strengths on the upper bound. You cannot, let's say, use these functions to generate independence results for ID1, except that you come up with normal forms which somehow destroys this immutability structure.
Yeah.
And of course, somehow by some tricky definition you can define everything, but what one wants to have is one wants to start with a basic set of operations. You define normal form with respect to number k. You abstract the k away by introducing a variable, and you use constants for the smaller ones. And you form a set of normal forms indexed by k. This forms a set tk, and then when you let k growing, you form the direct limit, and then hopefully you get a nice, well-ordered direct system, and then you apply this argument, which which is over there in our case, to show its termination. And maybe that's already enough to stop for today. So I have some more material. There's this other normal form which we used in the paper for Ackermann. We were using these normal forms of the form M is FA1 FAN EN of something. And all of these normal forms can be treated by this approach, but one has to be careful. The point is that if I use exponential function and many functions, they form terms. And if the k becomes larger than the norm of the term, then these terms are automatically in normal form for whatever reason. It's just this bit of effect. Now here it's not the case. So when you form such a term, and the norm of the term is when k is bigger than the norm of the term, it doesn't mean that this is a normal form. So one gets some extra complications because the idea here has to be, let me first define the normal form and then I will explain the problem. So the F hierarchy I'll define like this one. So let's say that 0 is n plus 1. As a plus 1 of n means I take as a iterated n plus 1 times by n. So very similar. Now, how to consider the norm form? Take m. Then first you approximate m from below. So you take you fix k. K is fixed. Now, if m is smaller than k, then m is its normal form. if m is equal to k, it's also still the normal form. To assume that m is bigger than k. Then m is approximated from below by such a function. That's the next thing. So I choose a maximal a1, but one gets this inequality. So a1 could be equal to 0. Let's say if n is k plus 1. Anyway, but there will be maximal a1 such as this holds. If a1 is fixed, one takes a maximal b1 such that with b1 iterations of a1 of f index a1 by k1 gets m, then something is happening. So this b1 has to be bounded by k plus 1, because if b1 would be k plus 1, you would a1 would not be maximal. Okay, so if b1 is maximal, there's a restriction of b1. And then you have from the next iteration, choose f, choose a2, so this is bounded by m. a2 is maximal, but this result is bounded by m. Then you choose a maximal b2, but this result is bounded by m. Then form this expression until you hit the number L, such as fa, L, this term. Some moment you will hit m. But what's the point here is you get the descending sequence of numbers. And so not all terms are in normal form, independent of how big the norm is. So somewhat important to have a descending sequence of numbers here for the normal forms. So to deal with these sets, you have to restrict the notion of what I did here. For the less than equal to k relation, one has to make some additional adjustments how to keep with this one. And now what is the point over here? Well, what is the underlying construction here? So what type of complexity can you basically assume? And it seems, it has been shown that this normal form leads to gamma 0 Now, what is now so you need two binary functions which are involved. So basically, it's AB going to FAB. And the other binary function which you need is composition. Then you can set up a formal set of terms modeling this, such that with such a function is a binary composition. You can generate immutability relations, and that can be used to prove termination of that system. When the b's here are fixed, and the b's here are fixed, you can get rid of this one. And then you have a function basically a plus 2 fa composed or something. And this is basically, well, something like this. And this is just a binary function. So when the b's here are fixed numbers, then you can go along with one binary operation, and then you get an epsilon 0 independence result. Okay, and that's a good moment to stop.
Yeah. Thank you. All right. So I have a question. So, I mean, of course, here you kind of use this this quasi-ordinate results of Schmidt, right? So, okay, restricted version of class. And of course, kind of what's crucial to apply them would be the fact that you're okay. Basically, you need two properties of the function. Namely, the function should be a monotone in all that, and secondly, they should be not increasing or at least not decreasing.
Yeah.
Yeah, no, but then of course, I mean, we know this other bulk, kind of much stronger bulk quasi-ordinate results. It is something like with say Friedman's version of classical theorem, right? And I believe this kind of should basically respond to the drop of the. Well, I think on increased condition that the function should necessarily be increasing. Something sometimes can be
Yes,
non-increasing.
yes, yes.
And but then yes, and then
Question is what to make of this.
yeah, I don't know. Do you have any ideas?
Yes,
What kind of number theory can be used here?
The point is we have this dot routine by Jeroen van der Westen. And basically, the point is you have to find a set of terms where you incorporate the F alpha.
Yes.
And basically, you have two data types, namely you have orders and numbers. And we have two different recapitulations. One is for the orders and one is for the terms.
Okay.
And then you can apply the result on what is introduced by Jeroen for the Howard-Bachmann ordinal.
Yeah.
It's basically trees of binary trees. So we have outer trees, so the FR, the inner trees are the ones coming from the orders.
Okay.
And that works. And so this argument would show that with the F alpha functions, you can, if alpha is smaller than epsilon 0, you can only generate the Howard ordinal, but not the bigger strings using Goodstein.
Okay. No, okay, sure. This is fine, but I guess it's not precisely the direction I was thinking about. So because I mean okay, this is kind of slightly it's kind of different setting, right? So when you indeed have this sophisticated some sort of very sophisticated algebra functions, or anyway, essentially, yeah, okay, you index functions by ordinals, and then you somehow need to do some sophisticated ordinal kind of base shifts and all. Yes, which is okay. So clearly does work, but it kind of produces fairly complicated Goodstein principles in that. But the kind of different approach, kind of that you can, at least this, I think, is being suggested by the much stronger about quasi-organized results would be the one where you kind of maybe perhaps you use some different kinds of number kind of functions on numbers that they kind of stop being increasing, right? So because this is basically what would be the kind of the big difference. That basically would make perhaps would land us in the situation when we still can apply Friedman's theorem, but no longer can apply kind of say Krasn's theorem.
Right.
But then, yeah, the problem is that because I have kind of I don't really know where to get these functions. I was trying to ask
that's a good question. I also don't know, but maybe it's an interesting research project, but it's a bit dangerous because I have no clear picture what.
Yeah.
Using different data structures for ordinals and terms, it's just business as usual.
Yeah, this I understand. Yeah, I don't know, but I guess because maybe we can kind of get something from number theory, right? Because in principle they do have this functions that are not increasing, right? Something like Euler function, and maybe. But I mean, I honestly I don't know that much number theory. I don't know like precisely where to go with this further.
Yeah, well, everything is open here.
Okay.
But just what I want to say is, one has this general feeling if you set up some stuff, you have always a clear idea that there's an upper bound for strengths what you can do with a given signature. And well partial orders gives precise context. This is somehow well, it's not a big surprise. And basically, what we do is we find a way to abstract away set parameter k by going to the limit. But this is also what you do in the ordinal assignment. So if you have to do the ordinal assignment, you get a plus b, ternary function, but the ordinals, which you're so taking is formula is the ordinal of a plus b. Something in the k is also true, right? And actually, I did basically the same over here.
Yes.
Basically, I formed this abstract limit, but what is happening, of course, finally, is when you look at it for the exponential terms, you get classical on the stack. But it's slightly more general because I'm speaking about abstract stuff. And the Ackermann function uses a different way of combination. Yeah, anyway. Are there people online?
No. Still do.
Nobody.
Do you have any other questions?
Okay.
Okay, yeah. Okay, thank you, Andreas. Yeah, so I think it was quite interesting.
Forgot to tell, this should be part of our joint paper.
Ah, yeah.
It would be fun.
Okay.
But today I didn't speak about finitary functors at all, so that's a different subject. The point here is with these, what you always see is you can move bases upwards.
Yes.
So
Yeah.
k goes to k plus 1, but you never see k goes to k minus 1. And that usually kills your normal form. When you start with the normal form and you make the base smaller, the new term exists, but it's no longer that nice.
Yes. Yeah, no, but I think that your after condition say okay, basically when you is talking about this kind of situations that terms eventually reach normal form. I mean, actually, it's not that dissimilar with what you kind of getting for this, say, normal form theorem from finite functors. So basically, again, my technique is slightly different there, so because the normal form theorem that we are planning to have in our joint paper, right? So this is the one where basically you kind of restrict situation when kind of term can be applied.
Yeah.
But then kind of basically the point is that from some point, like basically for each term, it could be applied starting from some point.
Yeah, but
yeah.
said in this situation, it does not work like this because there's this condition on monotonicity of the int.
Yeah, sure.
And of course, can form terms where this is destroyed. And the only way to apply Goodstein is first you take your term, you calculate the normal form with the intermixed indices, and then you start Goodstein.
Yes.
And actually, if a different order, actually calculating the normal form where you have this normal form, it's not even clear whether this is a primitive recursive procedure. Yeah.
So you mean
given term
and then going base shift and then -1? This is not maybe not.
No, just a term. Let's say example is we have few of
yeah.
What is the normal form?
I see.
This is easy from
I see.
And actually, it's not so obvious, right? Because we need not. This one is smaller than this one. So we have to calculate the value, and then we have to do the approximation procedure. But this uses a non-primitive recursive construction. Now the question is, giving a term like this one, can you move it by a primitive recursive procedure into the normal? It's not clear. I would guess the answer is yes, but at least you cannot do the trivial way of calculating the value and then applying the sandwich chain. That's a good question. So Arnold Beckmann once has written a paper in JSL. He was answering a question by Takeuchi, and he was also doing some sort of argument related to this. The Takeuchi was also suggesting, when you want to do this, you first to evaluate, and then you have to compare, and then you get to large complexity. Arnold said, no. You do something else, and his procedure was faster, and then he was answering the question of Takeuchi. But it's also not a good PhD topic. So we don't know the answer.
No. Actually, it's just quite hard to gauge the complexity of the question, right?
It would even be a trivial question.
No, I don't think it's trivial, but but it can be not very hard. Like maybe
it could be that somebody solves this in 1 week and says, look here.
Yes, but then it might happen to be very, very hard to solve. Really,
it will only be that after 5 years you don't have any progress.
No, this kind of question is certainly very possible.
Anyway.
Okay,
It was a sort of also give a talk which I gave already in Vienna, the one about logical limit laws. I have not given it in the seminar over here. So who has not heard about logical limit laws? You don't? You have seen it? You don't?
Not too much.
What?
don't really know too much about it.
And you have been in the end? So I think it's a nice topic, and the point is, I would like to give the logical limit law talk over this seminar because we are putting it on YouTube afterwards, and then people can listen from the outside.
Yes.
So I
Yeah.
could do it even next Thursday.
Next no, I think okay. We can
Or
check
this
us-
next week, and we have
Okay, maybe we end the recording at this point.